Okay, so the last thing we're going to be covering in our section on the Lagrangian formulation of mechanics is a proper in-depth derivation of the Euler-Lagrange equations. Now, nothing in this will be outside the scope of the course, but we'll really get into it and find a little bit of a nicer derivation than the one we used earlier. Okay, so the idea is that we have some Lagrangian such that the action S, which is equal to the integral from t naught to t1 of the Lagrangian, which in this case is going to be the most general. So we'll have qi, q dot, and t, ut. And this comes from if the energy, either tensor of the kinetic energy, has any explicit time dependence. So that's why we need to put our t in the Lagrangian as well here. Alright, so the idea is if we have, let's say, some space here, and our particle will map out a trajectory or an orbit from here, which it will be at t naught, and it will take some path that minimizes the action until it reaches t1. Now, we don't actually know this path, and it isn't really important that we do. The idea is that this will follow some trajectory. We'll call it q naught of t. Right, so that's taking some trajectory. This is the correct trajectory that it's taking, but we don't know what that is. But we'll assume it exists, and we'll say that instead of dealing with that directly, we'll take loads of different possible paths. So we'll say that there's some q sub a of t, some trajectory that is the actual path that it's taking, plus a times some beta of t, where a is just some real number, some constant. So what this means is, this means that beta evaluated at the endpoints, so t1 must equal beta of t1, or t naught must equal t1, which is equal to 0. So this means we're keeping our endpoints fixed, because at t1 and t naught, this part will go to 0, and we're just left with q naught of t naught or t1. So what this event is saying is that we'll have some different paths drawn out like this, depending on what A is, what A and B are rather, or A and beta. So this is, beta can be any function, it doesn't really matter what, and A can be any real number, such that beta of t naught is equal to beta of t1, which is equal to 0. Okay, so now that we have this, let's also take the time derivative. So we'll say that q sub a dot is equal to q sub naught dot plus a times beta dot. Okay, so now we have these tools, we can attack the action again. So when we had our action, we were saying that this is going to be minimized no matter what. But let's say that we want to see how much the action is affected by this A here. So this means that we're going to need to take the derivative of the action with respect to A, which, using Leibniz's rule for integration, we can bring the derivative sign inside to the integral. So we'll say this is the integral from t naught to t1 of dl dA dt. Alright, and now using the chain rule, we can say this is t naught to t1 of dl dq dA plus dl dq dot by dq dot dA dt. Because q and q dot both around A. Okay, so let's have a look at what dq dA is. So if we have dq dqa, just to make sure, just to be clarified, these here are the functions of q at a, right? So we have here dl dq sub a by dq sub a dA, and dl dq sub a dot by dq sub a dot dA. Okay, so now we have dq sub dot dA, dq sub a dA rather, and we'll see that this is just beta, and likewise if we have dq sub a dot dA, we'll find that this is just beta dot, okay? And swapping this back into our formula down here, we'll get that we have the integral from t0 to t1 of dl dq sub a by beta plus dl by dq sub a dot by beta dot dt. Okay, so now that we have this, we're going to go back to what we were learning at the beginning with our integration skills, and we're going to use a trick with integration by parts. Right, so we're going to take this second part of the integral here. Let's just move our integral up a bit. Right, so let's actually, I'll put this in blue just so we know that we're talking about really this part right now. Right, so we are going to if we remember the integration by part rule, which is the integral of a b of u dv is equal to uv evaluated at a and b minus the integral from a to b times v du. And I might have used different notation at the beginning, but it means the same thing. Okay. Now we have this sectioned off. Okay, so now using this, we can set beta dot equal to dv, and we'll be able to play around with it, and we'll get that dl dq dot a times beta evaluated at t0 and t1. This integral here, this blue integral, is equal to this minus the integral from t0 to t1 of d dt, so d dt of dl dq dot sub a times beta dt. Okay. Alright, so now we know from our boundary conditions here that this beta, when evaluated at t0 and t1, will go to 0. So we can say that this entire term will go to 0. And we're left that this is equal to the integral from t0 to t1 of d dt of the partial L with respect to q sub a dot times some beta dt. Alright, so this is now our new blue integral, which means if we take our original integral here and we'll bring it along here to the side, we'll get that this is now equal to the integral from t0 to t1 of, we'll get an open bracket here, dl dqa dl dqa minus d dt dl dq so a dot all times beta dt. Now for our definition, we said that this would always have to be equal to 0, right? This would always minimize the action. And so no matter what we choose beta to be, right? That's how we define it. And so this integral here is always 0, no matter what beta is, we can actually say that this part of the integrand here in the brackets must be equal to 0. No matter what beta is, or T0 and T1, and therefore we must say that dl dq sub a is equal to ddt dl dq sub a dot. Right. And now that we have, so now that we have this, we can assume it's taking its actual path here, so that when a equals 0, we have q0 down here, which is it's taking its actual path, because we're saying it all equals 0, which is indeed the Euler-Lagrange. So we have that proved in a much more mathematically rigorous way.